I'm very excited now to welcome you to this post-lunch session, which will start off with a keynote talk from Dr. Sonia. So Sonia is the General Manager of ITASCA Canada. She's a rock mechanics engineer, more than 20 years of experience in academia, consulting on various topics, rock mass characterization, slope design, mountain data interpretation, interaction analysis, numerical modeling for surface underground excavations. She's been involved in the design, operation, management, pit slopes, underground mines, civil works throughout North America and overseas. And as if that was not enough, she's also an adjunct professor at the University of British Columbia and Simon Fraser University. So please welcome Sonia for her presentation.
Thank you. So very humble today to be here, especially presenting after two superstars and superheroes on numerical modeling. And I'll let them debate on who is Superman and who is Batman. I was not going to make that call. But when I was invited to give this presentation, I started thinking about back at my early days when I started numerical modeling. Now, I didn't use punch card, but I use some pretty old-looking computers like this one. And as a reference, my daughter is turning 14 in August. She actually only seen that computer in a museum. So what is a familiar object to me is an artifact for her. Now, in my early days, this is when I studied numerical modeling. I started working on FLAC. I was doing a seismic analysis of a earth dam. And these are my colleagues, the few ones that have decided to do a thesis in numerical modeling. 5 of us in that picture, we're using ITASCA software. FLAC was just being released 2 years prior to when I started working on it. And we were all pretty tediously learning the software at that time. A couple of things I learned from that exercise was to pay attention to details because my analysis, not couple analysis, took 2 weeks to run. And after 2 weeks, I didn't want to find out that I put a comma in the wrong place and had to wait for another 2 weeks to get some results. So pretty tedious, but really taught me a good lesson. The other lesson that I learned was to simplify the models because even the location of history points made the model run longer. And so even understanding where did I needed the information, what questions I was trying to answer, where was it necessary to have a history points and where could I just keep it to keep the running time shorter was essential. That simplification of the model came really handy a few years later when I was working on a project and my supervisor at Boulder comes to me and says, Sonia, can you stop a glacier? And I thought that was a silly question, but my education was in Catholic school. And I don't mean to offend anyone with that. My answer was, well, I'm not Moses. I cannot part seas. I cannot stop glacier. What are you trying to do here? The project was actually very, very interesting. There is a mine, Kumtor mine in Kyrgyzstan, where they're excavating within 2 glaciers and then a south expansions in a 3rd glacier. Mm-hmm. And they literally had the glacier flowing into the open pit. They were trying to stop that from happening, find a better way to excavate where they didn't need to excavate ice at the top of the mine. So we said, okay, how are we going to do that? We said, well, the model, the maximum simplification of it is pretty simple. We have a layer of ice, we have some till, and then a bedrock. What if we put waste rock on top of the ice? The ice is going to creep, and the waste is going to sink in it and form a earth dam. So if we don't stop the glacier, maybe we just deviate it so it doesn't flow inside the pit, it flows sideways. Now, easy said, how do you model that? We were working in 2D at that time, not 3D analysis, and there is a lot of different parameters to consider, but our model was trimmed to the bones. Well, this was the model at that time. We had a little box, there was the waste dump, a layer of ice, layer of till, and that was it. And working long enough with glaciologists that really helped me setting those parameters, I learned a lot about cold ice and warm ice, and how the glacier moves at different velocity within its body, different velocity in each season. And all of that became parameters for the creep model in FLAC. I didn't even change the size of the waste dump in order to model the different volumes of waste rock to be dumped on the ice to allow that sinking in a certain time frame. I just changed the density of the material. So in simplification to the maximum. We were working in large strain, but even that wasn't sufficient for the deformation that the model was doing. So I actually had to take, after the first run, I had to take the geometry and input as an input in a new model. So I had to remesh the model and run a second simulation. Those two simulations combined, those results made into prediction charts. Unfortunately, I wasn't able to retrieve the data from the field that we had that showed how this prediction chart, despite the fact that the model was not calibrated, actually matched pretty well with the data of the sinking waste inside the glacier, inside the ice. And you can see a picture here of a cat with part of the waste rock inside the ice. So it was a really fun project. Now, what does simplification mean? Well, to me, simplification means, first of all, understanding which questions are we trying to answer. So do we need to include every single element in that model? For an open pit mine, for example, in a coal deposit, do we need every single coal seam? Doesn't matter if it's a high wall or a footwall. Well, probably does. If we're simulating a footwall, we want to know where those coal seams are with respect to the wall face. But if it's an high wall, maybe an ubiquitous joint function or a comba model, it would be good enough. So those questions really need to be answered before we start modeling. And those principles, I think, are going to stick with us forever. It's going to be there now, in the past, and in the future. What information do we have? If we don't have data, do we really want to go and try to simulate each coal seam or each interbed, interburden layer? Do we need a 2D or a 3D analysis? I really like a quote from Einstein that said, everything should be made as simple as possible, but not simpler. We can learn a lot from simple models and then use it in more sophisticated models. This example is a project that was done in Sweden. I think Johnny was involved. A 2D FLAC model was done where they looked at what key parameters were influencing the deformation of this excavation in mixed ground conditions, rock and soil. So when that was done, a few years after construction, a FLAC 3D model was built. The FLAC 3D model was informed on the findings of the FLAC 2D model, only included those elements that were already studied and understood to be necessary to properly simulate the behavior of that excavation. How far should the model extend? Are we looking at the global stability? Are we looking at the local stability? Are we looking at ground support? That is another important question to start answering. And what are the data that we're going to calibrate the model against? I'm showing a couple of images here on block caving, which is not been published yet. There's a paper that is coming up from Christian Kensino at the MASMIN conference in September. And in this particular case, the model was calibrated with TDR data and with smart markers in underground. So as the computer capability improves, we end up with models that are more and more complex. And at times, I've seen a complete disconnection between the modeling process and the reality of the world out there. We kind of forget to look around us and to make sure that our models are representing reality, and we've seen lots of talks about it. So one example that came back to mind was back at the time I was teaching at University of Rome, and I was teaching in civil engineering. So I was teaching foundation design. A student comes to me with a similar feature to this and announces, the formula you've given us, it's wrong. I get a negative value for the footing. And I'm like, okay, let me look at it. And he shows me this image. And I start asking, okay, what is that do? It's a 2 meter by 2 meter post. Okay, so 2 meter by 2 meter post, you have a load of 2 meganewton on a 2 meter by 2 meter post. So 2 meganewton is approximately the load of a 2-3 story building, which is exactly the size of the Department of Civil Engineering in the university we were in. So that was the building. We were in a room similar to this. And I asked him, look around you, do you see any 2 meter by 2 meter post? But there is not such a thing in a small building, right? 2 meganewton can be absolutely taken by footing that is much smaller than 2 by 2 meters. So the negative value was because the post was already much larger and the necessary footing to hold pressure. So this student, again, had demonstrated that I was so focused on the analysis that forgot to observe the reality of the world around it. I think the future will break through that, will allow the people who are out there in the field making the observation to really bring those observations into our modeling. After we have defined the objectives of the modeling, we're going to be, as usual, looking at the data that we have available, looking at what information we need in order to create a model. We'll find some gaps, which we need to fill somehow. So we're going to make some assumptions for the data that is missing. Those assumptions, with the model simplifications and the data that we have, are going to feed into a model that simulates the reality, including those field observations, so that we can have calibrated models. Those calibrated models, answers and solutions are going to be verified against the modeling results and the observations out there. If the modeling results and the observation match, great. We're in a good spot. We can be happy. We can be more confident in the results of the predictive modeling. This is an example of the eastern wall at Morenci Mine, the West Copper Pit, where we have a pretty good match of our modeling results with the deformations when a diabase seal is exposed at the toe of the slope with the radar monitoring data. What if it doesn't happen? What if the results don't match our observations? Well, we have to go back and look at the assumptions that we made, at the data that we have, potentially, regenerate the model, change it, modify, and go back into the loop. I think this exercise, and we have seen it, Chris, Jason, they all show some very good presentation in that regards how in the future, these observations, integration of the observations to our model is going to become more and more seamless. We're already doing it at ITASCA. We're taking, CPT, soil test, putting it in a cloud base, Jason just showed this, and integrating pretty much real time, being able to predict with 99% accuracy the soil bearing capacity. With that, it's impressive. I showed this one this morning as well, and then you showed it a couple of years ago at the Slope Stability Conference. We can look at a surrogate model that in 3 microseconds can predict the factor of safety for a slope of different geometry, different dimensions for the height, the interramp angle. Yes, it's not a precise tool, doesn't solve all the problems, but can give us some initial guidance for our design. The same for the waste ramp. So if you missed the presentation this morning, this is something really, really cool that we're already doing. And I think this is where the future is going. More of these easy to use tools for use and applications with integration of field data. CATS is one of our latest softwares. We can do probabilistic and deterministic analysis on any wall orientation with as many joint sets as you can dream of, essentially, and calculate on a radar plot. So visualize for all wall orientations, what are your critical failure mechanisms? What is your interramp angle, the bench face angle, the back break, spill length? Very visual, very good, again, for design. And not only that, for that part of integration of the observations, we can calibrate this design. So we can look at the data from existing benches, existing pit walls, and do that reconciliation, that calibration, modifying the input parameter to make sure that our design is not overly conservative or under conservative. And so what risk are we going to take? We're going to minimize that risk in the design by reconciling observations. We had the launch yesterday. I'm blown away. The more I find out of what it can do, and the more I'm blown away by this software, right? It's really fabulous tools for people who don't need to know how to script, don't need to know how to model, but they can use it efficiently and integrate, again, the data from the field into a very powerful tool. It works on seismic potency, which I understand is more reliable to correlate with seismic data. Because in our models, when we do especially frac 3D analysis, we dump the energy in the system. And so that correlation between the seismic energy monitoring in the field and the seismic energy in the model is not as reliable as it is with seismic potency. So again, a very incredible tool for that. So where the future is going to bring us? My opinion is more of this integration of real-time monitoring into the analysis to have near-time recalibrations of our model and answers. Easy to use tools. I show a few of them. We see more this morning that everybody can use. So that, again, that integration of the data and collaboration with people who are in the field, not just us behind the screen and the computer, can happen. AI, machine learning are gonna really help with that integration of the data. We've seen another couple of examples of machine learning for using geophysical data to recognize not just auto-picking of the structures, but classifying, recognizing what the difference between a foliation and a joint. We can use it, machine learning, to understand the rock mass properties from borehole data. So my opinion, the future of modeling at ITASCA is already here. Yes.
On the slide you showed 3D model. Does CATS have any interaction with 3D?
Not directly, but we can overlay and export the geometries of those wedges and import it into FLAC 3D. Yes.
CATS in the past. Maybe there are some new capabilities that have been developed.
Not yet. Yes.
When you go to actual sites and working with the real project, do you find people on site who are able to have a dialogue with you? Who have enough information and understanding of what you want to do to tell you what their observations are?
Well, I learned to talk to them, right? We use a different language sometimes. They are used to face risk in the operation. They want to keep equipment and people safe. So their point of view is sometimes different than ours. We want to understand the problem. Yeah. They want to make sure people are safe. So as far as we let them, or at least my approach has been, as far as we make them understand that our purpose ultimately with our analysis is the same as their purpose, to keep people safe in the operations, then there is a much better chance that they're gonna want to listen to the request for data modeling, why we are asking for that, right? So
because the point I was trying to make is that we need, talking primarily from the United States point of view, I think it's applicable. It's not just the type of people that ITASCA has in-house. The type of people, perhaps at, let's say at the university at a master's degree level, they're going to come in and have the responsibility to make that mine profitable, but have, and currently, most schools are deficient in enrollment in mining engineering. But if you look at the problems and look at actually the people who come into something like ITASCA, they come from all disciplines.
Mm-hmm.
The latest acquisition of one of somebody, different branch of physics. But so the input is going to come in the future from in ITASCA, totally interdisciplinary. So there's needs for the researcher, but also a group of people in mines who are already predisposed to attacking problems with an awareness of what you and others, which I think is excellent, by the way, are doing. So that's a goal that I think through educational that we need to pursue.
Yeah, I tried. I thought so. The 2 years I was teaching at UBC, I was teaching the capstone, and my goal was to bring real projects at the university level so that the students could actually work with mining companies on problems that the mining companies were facing and trying to solve those problems. Because I think you're right, there is a gap between the university and the academia right now and the industry, and we're kind of being sometimes a little bit too much on the academic side, I think. So, well, thank you.
Thank you, Sonia.